Welcome to this video on superposition of electric fields. Again, another mathematical example of adding electric field vectors. And in this example, I want to find the net electric field at this point over here, and that point on the Cartesian plane is 5, 3. And I want to know what the net electric field is going to be right there. And so we're going to figure that out in this video. Now what we want to do is say, what is the direction of the electric field at that point due to each of the two charged particles? This particle on the left is QA, this one on the right is QB, and again I'm going to say, for us to start here, that the magnitude of QA and QB are equal. So the part that's electrostatics set up here, and not just pure vector addition, is determining what the direction of the electric field is at that point. So what I'm going to do is I'm going to go ahead and draw that in, and I'm only going to pick one vector that's directly away from QA, and I'm going to sketch that vector in like this, and I'm going to label that one EA at that point, and similarly I would have EB over here that's being contributed from QB, and I have those two vectors. So essentially what this problem is now is that I'm adding EB and EA together, but EB and EA are not directly opposite one another. They are now at an angle to one another. Originally in the previous problem I had at this position over here, which was 5, 0, EA happened to be exactly opposite EB, and that was easy because I just ended up having to subtract them. Now what I'm going to have to do is figure out what EA and EB are, but I'm first going to have to break them up into components. So what I'm going to show is that EA has an X component and a Y component, as does EB. It's very clear that the X components cancel out because they're pointing in opposite directions with an equal magnitude, so it's really just a mirror image or a symmetry of this situation over here. So I can still write that out, and I'm going to write it out just so we can make sure that we know that if it wasn't exactly the same value of QA and QB were not equal to each other, that you could still solve this problem. So I'll write EB on the left here. I'm going to do EB in the X, which actually ends up being negative, so let me go ahead and just scoot that around. I'm going to go ahead and say EA in the X minus EB in the X is going to give me 0 because they're equal magnitude, opposite directions, and you can watch the previous video if you need to look at that again. The other one, what I'm going to have to do here is I'm going to add EB in the Y and EA in the Y, and that's going to give me the net electric field in the Y dimension, and because the net electric field in the X dimension is 0, this happens to just be the net total, which would be great. So what I'm doing here essentially in this problem is really just focusing on EBY and EAY. So let's figure out what component of these two is a contribution from each of QA and QB. So this happens to be actually a lot easier of a problem to do because of the symmetry that's involved. Alright, and so if I sketch this out here, I know the height of this triangle is 3, and each of the distances to this middle point here is also 3. So I have an isosceles triangle, alright, and that's going to allow me to use opposite angles here to say that this is 45, and of course this also has to be 45. So I can use sine or cosine here to get the component of EA and EB that is pointing up in the Y direction. The main point is that they're both pointing up, so they get added rather than in the X direction where one points to the right, one points to the left. It means they get deleted or canceled out. So what I'm going to do here is write EB in the Y is really EB sine of 45 degrees. And I'm going to add that to EA in the Y, which is EA sine of 45 degrees. And that will give me my value. Now, because QA equals QB, I also know that EA has to equal EB because those two have the same magnitude and this is a symmetrical situation. So what ends up happening here is I just end up with doubling the value of either EA or EB times the sine of 45 degrees, and then I'll have the value of the electric field at that point. Now, of course, if QA and QB are not equal and this point shifts over a little bit, it means that I'm going to get a value here that will not be 0, and I'll get my E net Y that will not be 0. And I'll have to take those two values in one additional step, take my E net in the X squared plus my E net in the Y squared, and use the Pythagorean theorem to give me my E net direction. Additionally, I would also need to use an inverse trig sign in order to get an angle at which the net electric field would be directed. In this case over here, the net electric field is just going to be pointing straight up in the positive y direction, and so you can see that it's not even necessary for me to have an angle. So I hope that helps. And when you do these problems, no matter how many charged particles you have, you can just find the x and the y components of each, add all the x's, add all the y's, and then add them using the Pythagorean theorem to get your resultant vector. Always try to look for symmetry because that can help solve the problem and make your life a lot easier and be much less time consuming.